I have a wide agenda, it seems like today. So what I wanted to do is, because I did give a seminar earlier on when I visited, started in September, but I wanted to give you a broader overview of what I do. So this talk, I'm going to make sure to give a bird's eye view of three different kinds of work, three different application areas, three different methodological areas as well, in terms of how the methods come together in each of these realms. And that's why I thought I'll highlight in order to show some sort of variety of the kind of things and hopefully spur some new collaborations out here. So what I'll do therefore is not to go too deep mathematically into one particular problem. What I'll do is give an idea of here's the problem, here's what we hope to do, and here are the two key ideas that a method does in that particular problem realm, and here are the impact and insights. And that's really how I want to talk about all the three verticals, so to speak, and then we'll hopefully have some discussion. What I work on is trying to build algorithms that are computationally efficient for systems that are designed as networks. And these networks are fundamentally subject to uncertainty, and I focus on the uncertainty part. And how do you actually tackle that uncertainty in multiple different ways? Every system has its own way, and in that as well, depending on the kinds of objectives, stakeholders, what have you. And so I look at how do you combine different methodologies, different kinds of ideas, and so on, in order to make sure that you're building new computationally efficient approaches that at the same time rigorously you're able to trade off between accuracy and computational efficiency as needed, so that you can actually solve and operate for these large-scale network systems under uncertainty. And something to remember is that these systems are pretty large scale. So even to solve the deterministic versions of these problems has traditionally taken a great deal of effort. So we're looking at not only the fact that they are deterministically hard, but at the same time, you're looking at nonlinear costs. You have this idea that since it's a network, something that happens in one part of the network actually propagates somewhere else, which means that you have to actually think of the network as a system and not as just a disconnected set of pieces, right? And explicitly capturing some of that. And also thinking about the kinds of multiple heterogeneous and discrete resources. So when you have discrete decisions, often making these decisions and simultaneously making and quantifying these trade-offs that I spoke about is actually much harder. So how do you do that in the presence of these discrete decisions? Right. And the kind of applications I'm looking at is pretty much all over the place, but like I like mobility-based systems a lot. And so a lot of the work comes from airlines, logistics carriers, from emergency services, on-demand type of networks, as well as cyber-physical systems when you think about applications like land security, UAV mission management, and so on. So I would think of some of these applications and settings as settings where you actually have schedule-based services, where you have to operate, or you're published, the operator publishes a schedule, and the demand kind of meets the schedule. Another set of these problems are on demand, where you have emergency services, ride-hailing, and so on. You really have to respond. Your capacity has to be responsive to demand. Right? So essentially, it's a different kind of push-pull in a sense, in terms of how these systems are defined and how they are designed as well. So how much control the operator has in terms of designing often influences, and how much endogeneity is there between supply and demand is slightly varies across these different systems. And we won't get into the depths of that, but just to give you a broad idea. My personal research philosophy is to think about the real data, work with operators in the field, discover the problem by looking at the data and coming up with whether this data, the problem that is specified is indeed reflected in the data. And does the data either show something else, or does it describe the uncertainty in a different way, describe the problem itself in a different way, and so on. So we collect that data. And then I tend to also build new methodology that bridges these different fields. And then finally come up with the right impact and insights for how do we learn about these different problems, how do we solve for them, and what are the eventual things. So these are the two research streams that I spoke about. I'm just going to jump across so we can get to the three different settings that I mentioned. The first one is going to talk about airline recovery. So a lot of you have been subject to the vagaries of the airlines, right? Aviation system in broadly speaking, but also how airlines manage and operate their schedules. So you would have seen that there are ways that the airlines will actually, as a passenger, if there is any disruption, they'll say, okay, we're going to move you to a different flight. Or potentially you're still sitting at the gate and the crew member is a different crew member, or the plane is a different plane, and so on. You would have seen multiple of these happen if you're sitting in an airport and your flight is potentially delayed. Right? So I'm looking at, in this, I'll talk a little bit about understanding how to do airline recovery. What the process of recovery is what is called disruption management or irregular operations. A few different terms are used in the industry for that. What it basically means is that you have a schedule that you plan to operate. Right? This falls under the stream that I said. You have a planned schedule. You're trying to serve people based off of some plan that the operator already has in place. This is in contrast to on-demand systems where there's no plan. So this plan is what you're trying to get back to when you're saying recovery, right? That's essentially what you're trying to do. If one flight is cancelled or delayed, you're trying to say, let's make sure the rest of the flight or as little of the future flights or passengers or crew are disrupted. That's essentially the word recovery, as simple as that. So it's very hard to do, however. Now, the reasons for the disruption are one of them, and the other being how do you actually manage the amount of leeway available in management and so on. Another is also that in terms of people have never known how performance bounds, how to measure the impact and value of recovery. And that's something that my work actually helps people do at this point. In fact, how better can we predict things? So let me give you some idea of how this works. Okay. So a little bit of the math. So what I'll tell you a little bit about is one of the baseline myopic recovery is what is currently used in practice. Just from a philosophical point of view, what airlines do is to say, currently, I have information about the state of my system. I know where my planes are, my people are, and people meaning both crew as well as passengers. I need to move everything in the system so that I can get back to as close to normal as possible and as fast as possible with the least cost. And often as close as possible is really a proxy for as cheaply as, right, as fast as. That's really the idea. But what airlines do is do it myopically. That means they know so far the status of the system. That means the past. They assume the future you have no information about and just say, I'm going to plan for the fact that the system has to come back onto track. What we do, and there's another paper of mine a little bit way back on actually combining what's called trajectory optimization with recovery. So if you can actually change flight speeds, you can do better. Now, the work that I'll talk to you more about is this SDRPN. It's called stochastic dynamic proactive and reactive disruption management. It's a combination of proactive and reactive. So what does this mean? The traditional method, the baseline that airlines typically do is what is called reactive. They see the past and then they say, oh, I have to recover from this. They made mistakes or we've been subject to different kinds of weather or other considerations. Let me try to recover. Now, what we do is to say, if I want to be both reactive and proactive, I see the past, but I'm also going to say, I've seen what happened so far, and I want to plan for the future. That means I have to take certain actions to recover the past But I'm also going to make certain predictions about what the future might entail. For example, in our case, what we do is we'll also predict which airports, in particular, which hub airports are going to experience what kind of delays or what patterns of delays, right? We're going to incorporate that as we recover, as we build our recovery policies, which have to be online, right? They have to be evolving. For example, every hour you have to be monitoring the system, especially during high traffic, high congestion, or bad weather consideration, and say, can I recover from this? So if I actually combine these things and say, I'm not only going to take the past into consideration, but know that the future, wherever these planes are going to go in my recovery decisions, also they will be subject to some amount of uncertainty. Then I'm being both reactive and proactive. Now, here comes one interesting thing. I need information in order to be proactive, right? I need good predictions. If my predictions are bad, my decisions will be bad. So it's not necessary that proactiveness is always good, right? And therefore the question is, what is the quality of my information, right? The other question is, one is quality of information. The other is, how much better can I do? Can I keep getting better and better quality of information? Or is there a limit? I'm going to hit a wall at some point and I can't do better, no matter what, right? And that's essentially what these pieces of work really help answer. So this other work will actually say, there's an idea of penalized regret, of saying, here is the bound, the limit that you can hit in terms of cost. So if here is my cost on myopic recovery, this is high. We've shown that the cost of proactive and reactive, joint proactive, reactive recovery is going to be a little lower, right, than that cost. So we get better. On the other hand, if I knew the entire future, perhaps I would get this, but that's a bound. That's a regret bound often used in the machine learning world. But of course, we'll never know the future perfectly. But we come up with another model, which is called penalized regret, which says, given that, assuming that I can only know certain things about the future, or I can only know predictions about the future, how well can I do? That's an information-based bound. That tells me, like, what is the wall I'm going to hit, right? That means I can never do better than that. And we can never, of course, do better than that. But I can even get better and say, no matter how much information or good predictions you have, this is the bound, and you needn't work with a very loose bound. This helps us quantify a bunch of other things. So again, there's this problem, method, and impact convergence in this project as well. So I'm just going to give you again a brief idea. What happens is, let's say you've got these airports, A, B, C, D, and I'm moving from left to right in time. So I start at time 0, and this is the end of the day, let's say. The black aircraft is doing flight 0, flight 1, then flight 2, flight 3, and flight 4. The red aircraft is doing flight 5, 6, 7, 8. Right? So essentially, I'm now these dotted lines, and this is the movement of a flight F0. I start at this time at B and end up at this other time at A. Therefore, always moving left, right. The dotted lines are potential recovery movements. That means if I delay by a little bit, if I change something else, what happens? Here, I indicate if the black aircraft, after coming to F1, instead of operating F2, suppose I ask it to operate F7, I'm doing what's called a swap. I'm changing the aircraft tail number that's doing each flight. These are all recovery actions. And there are fancy models to do this. This is a stochastic dynamic programming framework. I won't get into it, but that's what can be done. And you can come up with a nice rolling horizon model for all of this. So like I said, I have my original time frame. What we also do is to say, in this, I look ahead a little bit in this time frame TLA and say, here I'm going to incorporate some information. And this information is coming from airports. This is coming from a queuing model at each airport of how much traffic this airport is going to see in that time frame that we are looking at. So I'm not going to the math here, but it looks like there's a Markov chain, there is amount of how many planes are in queue at each airport and so on. Therefore, how much congestion will they experience? And so if you look at, let's say, deltas hubs, at each of the hubs, we have a pattern of predicted delay, right? So this is the amount of delay. I'm going to experience in each time frame of interest at each of Delta's hubs. So what we are going to do is not only look at the past information as to if Delta is doing its recovery process, what has happened to its passengers, crew, and aircraft so far, but also at every hub, what is likely to be the anticipated level of congestion in the next few hours. Capture that upfront and create a stochastic dynamic recovery frame, right? So essentially we capture that. So we are sort of putting all of these things together. We are doing dynamic recovery. We're saying capture this new notion of stochasticity and build this new model, right? Okay, I'll jump over the math for now. So we have this look ahead model. Now, the question becomes, yes, Eugene.
Can I just a clarifying question?
Yeah.
Do your decisions that you make have any effect on this like delay distribution, or the delay distribution just like fixed?
Good question. For now, we assume the delay distribution is fixed. Because we're looking at it in aggregate in some sense, because at every airport, it's coming from sort of a game theoretic perspective, like one individual flight will not change the overall distribution. But yes, it could happen if you took a very large airport, or if this was a large number of operations in that particular hour, for instance. So that's a good question. It's important here because I mean here we can ignore it simply because of the one aircraft type of. I'll tell you offline about some other reasons. Yeah. Okay. So we can just assume that we know the delay distributions upfront for that future time window and write the stochastic programming framework. So we've got this entire thing set up. Now the question becomes, well, I've got these predictions of what might happen. And these predictions are captured probabilistically because we don't know the future perfectly. Right? Now, is this information good enough is one question. Is this enough to help me do better? And how much better is one? And if I keep improving this information, will I keep getting better and better? And like I said, or will we hit a wall? That's another question. So we come up with another method, which is called information bounds. It was originally proposed by Brown, Smith, and Son, but the approach that they proposed involved state enumeration and dynamic programming, which turned out to be impractical for the kind of stochastic, dynamic, integer programs that we are interested in. So essentially what we said was, okay, we have a nice method, but we're going to expand it. We're going to do something cleverer. So I'm actually going to take that whole dynamic program, write the penalty function on the dynamic program for how much is information valuable is what that is trying to compute in short. What we do is to say, for every state, you need not compute, as they suggest, need not compute the value of that information, or conversely, what's called a penalty or regret of knowing too much information by a omniscient bound. What we say is, instead of capturing every single state, what I'm going to do is capture this value of information kind of function, but I'm going to do that implicitly instead of explicitly. They ask us to do it explicitly so that you can find again that performance bound, which is penalizing some omniscient, somebody who knows the future perfectly. What we are saying is, yes, we're going to penalize them, but we're going to penalize them implicitly. That means I'm not going to list all the states. I'm going to say at every state, here is the amount of information that they know in excess for which they have to be penalized because it's a performance bound. And I'm going to write that as an integer program as opposed to write that as a separate value function at every state independently. Yes.
Why exactly are they penalized for knowing too much information?
Because it's a good question, because it's a performance bound. So let's think about it. A normal performance bound is something on information. It's something that says, if I knew the future upfront at time t equal to 0, how well would I have done and what would have been my cost? This is your standard regret bound using machine learning, right? It's an online problem. That means as time passes, every hour or every decision point is when I make a new decision. Therefore, we are online. I get new information, and I keep repeating. So I'm working under partial information as the world reveals itself to me. Correct? Now that the regret bound doesn't do. It says, I know everything, right? And therefore, I'm going to give you the least cost set of decisions and therefore the least cost objective function that I could possibly achieve. What we are saying is, yes, that tells you a lot in some ways, but it also says that that's the perfect world. You could never achieve that perfect world. Like I drew that picture earlier on, which is the omniscient one was way on the left. I'm never going to be able to achieve that minimum cost. Therefore, I'm going to penalize that omniscient regret bound for knowing too much. You cannot ever know that much. So based on the type of information that might have, we're going to say penalize them. And we know that even they can do perfectly well, but no agent that has only myopic information can ever do that well. And we're able to say through these penalty functions, how well can any agent with only myopic information, whether they have predictions, stochastic predictions or whatever, how well can they possibly do? That's the wall that they're going to hit no matter how good a prediction you have, right? But some of the past theory on this said, write it as a dynamic program, list all the states of this problem, and try now at every state to enumerate, to penalize any omniscient planner, right? Does that make sense? So think about every possible state that the system can achieve, and every possible state, figure out that the omniscient planner knows too much and create a value function for how much they should be penalized. Right? It's a dynamic program that's sort of in reverse. Still a value function, but we're looking at penalizing it using a value. Now, writing a value function in theory might be easy, but to actually compute it for all the states that you think about in an airline network, for example, think about all your fleet of aircraft, the possible configurations of where they all might be at any point in time, that's your set of states, right? The amount of delay they're all experiencing, which is another set of states, right? It's a multi-dimensional state variable. Now, when you start to think about these multi-dimensional state variables, this blows up. There is no way we can first enumerate all the states. Second, then compute the penalty functions for every one of these states in a reliable fashion. So what we do is, forget about it. What we're going to do is find this penalty regret function, information-based regret, in a clever way by computing that value function that I spoke about, but in an implicit fashion. I compute that particular value function also as a time-space network. So like I showed you the time-space network a little bit ahead before this. This is the network I showed you. I can capture that penalty also on this network. There's a little bit of a trade-off that we make in terms of accuracy, but for a small amount of accuracy that we sacrifice, we get a huge amount of computational efficiency. And because of that, what happens is all of a sudden now I'm able to solve this problem without enumerating all the states and as an integer program. In fact, a series of nested integer programs. And what that tells me is, let me jump forward. So this is the way we capture it, how information can be captured. So I'm going to jump across that also a little bit. But it gives you a simple integer program to say this is nested within the original integer program for stochastic recovery. Now, what this gives you is something like a multi-stage recourse framework. Everybody knows stochastic programming, two-stage stochastic programming, for instance. It looks like that. So it looks like, here's my original problem. Plus, I've got these penalty functions written as integer programs as a subset of these integer programs. So we've got a nested integer program at each decision point. And now all of a sudden, I can say, boom, just solve it as a series of integer programs because they've spent a lot of time trying to figure out clever ways to solve large integer programs. So instead of solving complicated dynamic programs which we never end up solving well. We are instead solving an equivalent problem and being able to solve it tractably. Right? So we looked at, say, Delta Airlines network, collected data from Bureau of Transportation Statistics. And we said, if you capture this information at multiple hubs of this airline, how well can you do? We said, every time you capture information at, say, 3 hubs versus 6 hubs, you're doing better if you're capturing more and more information. So that's good. We said, the more information you capture for the future, the more look ahead you can have, the better you can do. Good. Now, and we said, if you can look ahead better, like 4 hours instead of 2 hours, even then that's good. That means, again, more information is helping us, right? And I'm going to skip over some of the nitty-gritties, but it does tell you that cancellations are reduced. Fundamentally, the impact is that I'm going to reduce the amount of delay, the amount of cancellations of flights that you will incur, because I am able to look into the future and know that the flight that I'm going to dispatch will encounter certain future delay. Knowing that, I'm going to make better decisions, right? So we're going to do selective swaps, not swap aircraft more non-intuitively, but do it with a knowledge of how much delay they will encounter in the future, or estimate of that, right? So let me, even this works under severe weather conditions. Every case we're able to reduce the cost by 3%, 2%, and so on. And these are large numbers in an airline industry where margins are approximately only about 2%. Okay, so we want to keep this in context of how much this cost might actually be in terms of experience, right? The other part is also that now, if I said I looked ahead, I have this information. Now, how much does this information help? And if I build better and better predictive models, am I getting better? We don't know yet. So now what we did was, for each of the fleet types, we're able to come up with this penalized regret, which means that this tells you, compared to if I looked at the machine learning bound, and my penalized regret bound, my better bound is 10% better, or 13% better, or 5% better for those particular networks. So that's one part of the puzzle. That means we're getting better bounds. That's one story. Now, what does that mean in terms of information? If I measured this, my look ahead model that I showed you with predictions, and I said I measured that against the omniscient bound, the normal regret bound, I would say I improved, I bridged the gap by 1.7%, or 8.43%, or 67%, or 3.67% in those particular networks. But remember, I showed you that we built a new bound, which is also tight, but it's a better bound. If I find that bound, it immediately tells me that the same predictions that I used actually bridge 3.5%, or 29%, or 71% of the gap, not what I thought before, but they're bridging a larger amount of the gap. That means, in general, that information that I had is actually better than I anticipated. Right? Every time I'm collecting some information, that's actually helping me more than I anticipate. But I also know that I cannot bridge, for example, in this network, I've already bridged 55% of possible gap. There's no way I can get more than that. So even no matter how much money you invest in good predictions, you can only do another 40% or so, right? And therefore you can make the trade-off. Now, do I want to invest my money in getting better predictions, doing something else, building some other more infrastructure, and so on, right? Okay, so that's essentially telling us that good predictions help, but to what extent, and where do we stop, right? So that's the first problem. And in fact, this solves an open problem in even this kind of bounds when we apply them to the emergency medical services literature. It turns out that people had stated some of this to be an open problem, and these actually help solve that open problem and answer that, in fact, something that was previously conceived as we can't address or solve it, we can, and we can say when it works and how, right? Also tells us in terms of impacts. Airlines and airports sharing information, very beneficial. We don't want to go too deep into how, but how do you share this real-time queuing or delay information? That's partly where the FAA needs to step in and do other work, but we are showing where the value is and to what extent, The bounds really help to say, see, we're able to recover 50% of costs in certain cases. That's a huge saving. The moment you're able to quantify to that extent, immediately it creates a case for like how much cooperation is valuable. Okay, so I don't have a whole lot of time, but in these settings, the second one in terms of airline pricing, I'm again going to give you a very high level overview and maybe maybe you can combine it to my office to ask deeper questions. In this setting, the question was, can we use a combination of machine learning and OR to make predictions so that I can actually price airline ancillaries at an individual level? We worked on ancillaries, but you could look at almost any product. And can these predictions that we have be converted to good individual decisions, personalized things? And if we have multiple types of agents or models, how do we choose them in a dynamic environment? So we built multiple classes of pricing models. Often the current standard of industry practice is that the rules are curated by a human. So how much to charge somebody for a bag or extra leg room and so on, this was just built in somewhat random way. Now we created machine learning models that are two-stage models, ancillary purchase prediction. We have a predictive model followed by a decision-making model using Gaussian knife-based or deep neural networks. And we have an end-to-end neural network that helps us figure out what is the probability that a particular passenger who just stepped into your system and started browsing through your offerings, what is the chance that they will purchase at a particular price? And over a series of prices now to say, what should I offer? And the nice thing is the information that we're using here is purely based on that particular passenger. What did they do in only that particular purchase? That means we don't have any demographic information about them from the past. Right now, what did you browse? What did you click on? What seemed more attractive in a sense? And therefore, can we offer you something that seems more reasonable for your particular choice, right? And we found that the deep neural network, the end-to-end deep neural network outperforms many of the other traditional models, including the sequential prediction and then optimization models. And we set this up on the airline website. We have an A/B testing framework. We looked at what's the price recommendation from the model, tested that on different passengers, how are passengers routed across these. We had a rigorous way of saying, how is the A/B test even set up in online? And how do we build this scalable ML model? And when we get customer feedback, did they purchase or not? And so on, how do we feed that back into the system? Right. And this is how it was presented on the airline's website, what happened at each step, when did the passengers see information, when did they see the ancillary, and then when did they see the actual, they were told that you may be offered a modified price. When we say modified, they were always offered, let's say your bag is always $25. They were offered less than 20. But how much less than 25? Depended on our algorithm. So people were like, okay, we are fine paying less than what we anticipate. Maybe somebody pays $5 less, maybe somebody pays $7 less, right? So they were happy with that. So it was presented in that way. And then we got that information, got the ground truth, and then circled that. And it resulted in 25% increased revenue per offer and 17% higher conversion. So that we turned out that the airline made money without violating price. And also at the same time, it was win-win for the passengers because whatever they wanted to purchase, they were offered something that they seemed to want to purchase. So these both are measures of both airline satisfaction and customer satisfaction. And we had an adaptive model framework to say, now if we have multiple agents, either multiple ancillaries, so somebody selling one agent, AI agent is selling legroom, another AI agent is selling seats, another AI agent selling bags. Now, among these, how do you choose between them? So we can actually, again, build a model selection framework for how do you route people to these different things, which selection of AI agents should you exhibit to each passengers so that you get better revenues. In fact, we in this case, we did this all for bags. So across different models that give you different recommendations, how do you actually pick? It's like each of these models are chosen using a multi-armed bandit framework to say which model eventually turns out to be the winner. But the winner is not a static winner, it's a dynamic one. So you're learning still over time. For example, if something like COVID strikes, we found that all of these patterns go away, you have to relearn. All the models have to relearn. Plus, which model is the winner also you have to relearn, right? So you really have to keep this going dynamically, not figure out one is static and then forget about it. You don't have real stationarity to speak of. Then I will end with a quick intro to some of the emergency service work that we've been doing. This is a city in India from which we got data. Some of the models that we developed, not the drone models, but some of the emergency service location models are being implemented in the state of Tamil Nadu in conjunction with the World Bank. So this work is about using drones to send quicker response to people. And this is a picture of Toronto, actually the region around, in Vancouver. And then this coordination is being tested in Toronto and Sweden. And what happens in these cases is that you're trying to address very, very highly sensitive emergencies by equipping drones with small kits, which have a EpiPen, a defibrillator. We have these very, very portable defibrillators that don't harm a living, breathing person, but do help a person who, let's say, has fibrillated arteries. So essentially, you have the medical equipment and a small kit, and drone can quickly take it there. Before, even faster than an ambulance, right? But you want somebody at the location there, either the person who called 911 or somebody else, a volunteer, a trained volunteer, to come and actually administer that service. So we're now looking at community-based emergency response. How do we deliver that in a reliable, safe, and efficient way, better than simply only having ambulances, right? So if we have trained people or if we have the bystander, in fact, we found that that's often efficient, even in terms of cardiac arrest. If somebody helps or does CPR or puts a defibrillator on their heart and presses the button, that's way better. And so we are looking at how do you actually now make this happen? Can we actually, how do we locate the drones? If I have a set of ambulance size, or if I want to redesign this network, how does that happen? What is the most efficient way? And how do we prove all of these things? And it turns out it's not simply this illustrative example to simply say it's not that I can just throw on the existing ambulance network a bunch of drones and hope people will turn up in terms of community response. In fact, we have to carefully calibrate where are community responders higher or more likely to come, where are drones likely to be more responsive and therefore more effective. All of that, unless we calibrate carefully, we'll actually get a bad system, right? And again, the same problem, method, impact, convergence. So I'll jump over the math of it. But what essentially turns out is that we build a model by which essentially what you're seeing is a picture where, in brief, the idea is that the drones can travel faster, right? But they have smaller ranges in a sense. So what the idea is try and spread out the drones across the system more, but also in regions where bystanders are likely to respond fast, right? That means the combination of a drone and a bystander is likely to be effective for quick response in those regions. Simultaneously, what we also want to do is what we call pooling of ambulances. Earlier, we also distributed ambulances geographically in order to make sure that response times were respected. But pooling has an advantage. Pooling actually increases availability of servers. So what we are doing, especially when it comes to spatial considerations, is actually this trade-off, this clever trade-off between one type of server you actually try to pool in an intelligent way where ambulances are going to be more efficient. Right? Ambulances being more efficient, meaning that drones are probably not, there's not very high bystander response. Drones can get there, but therefore they won't be too effective. Keep more ambulances there. In the regions where drones are likely to be more effective, because bystanders respond quickly, put more drones, spread them out there a lot more, and ambulances can go there a bit later. That means the first response is done by the drone and the bystander, the ambulance goes, picks the patient up and transports them to the hospital. So we are sort of distributing who does first response, in a sense, in a clever way, so that overall, across the entire region, you're actually achieving better outcomes for people. Right? So that's roughly the broad idea. Now you can get deeper in terms of like what is the exact trade-offs, how sensitive is the system with respect to bystander response, or even our estimates of bystander response. If I overestimate or underestimate bystander response, what happens? What happens with respect to different metrics? How quickly do you respond within a threshold or within expected service time? And also with respect to urban, rural, or semi-urban regions. So each region, in fact, we found that different models or different metrics seem to do better in different regions using these policies. Right? So so if we can improve availability of servers by actually positioning these ambulances and drones in these clever ways, right? The most benefit of having the drones is actually seen in rural areas, right? As you would expect. You'd want to say that rural areas are where ambulances, unfortunately, there are fewer ambulances for rural areas. They tend to be now spread out more and therefore have longer response times. Therefore, if you can quickly respond in those areas, and then even if ambulances take a bit longer, you have extended the patient's survival window in a sense. Okay, so I'll stop there. I didn't get to go too deep into the methods, but we can discuss any of those offline, and I'm happy to do so. Any questions? Since we started a bit late, I'm happy to hang around. Yeah.
So my question is about the regret penalty that you have to apply for the conjoined pooling for the drone and the ambulance service.
Okay, a regret penalty maybe?
So my hypothesis is that your benefits are likely increased, but they are stochastic. And so then could you end up in a situation wherever your aggregate scenario is improved, and on the aggregate you receive faster response time, aggregate better health outcomes, but could you experience individuals who have worse health outcomes because of this organization, and then how do you manage that in a bioethics sense?
That's a really good question. So we don't have a single answer, right? Because we're still looking at how this would play out. So all our simulations are studying the combined. So here's one part to that answer. One answer to that question is we're looking at what's called a robust measure of how to even look at bystander response as well as drone services, right? So once we actually have a more robust system, we're able to say who again is affected more or less and so on. And also to what extent, what is the worst case? How is the worst case effect, right? But again, we are not able to get to the level of granularity that you speak of in terms of, let's say, a single patient in, let's say, this grid of the city. How are they affected? We haven't gone to that far. We're able to say, however, is how is that worst case patient impacted, right? So the way we are measuring it is coming from a sort of a robust optimization perspective in terms of minimize the loss in the worst case, right? So yes, that's our second stage, which I did not speak of in this talk, and we are working on that. And yes, it is not easy to do, and I would imagine that the impact of this, like as we're talking to say the folks in Toronto, one of the suburbs, PU and so on, it's not going to be easy to just say yes, we'll roll it out and it'll all take care of it. I agree, but the overall, I guess, overall decision is compelling enough to say there's a case for doing this and where. And therefore, the question now is like to isolate the where first, so that you really get impact where you need it, and then roll it out in a more application.
So for your prediction of disruption and for the time space network, are you considering the hub and spoke network, and would it behave differently? Networks?
That's a good question. So far, we looked at this in a broad sense of saying what is a prediction and what type of predictions would be good for what kind of network. Since it was a hub and spoke airline, a hub-based prediction and the congestion levels at the hubs was the most natural way to think. But let's say I was looking at Southwest's network. I would look at it differently. Maybe certain hubs, but also what is the highest cause of uncertainty for some, right? For most hub and spoke airlines, it's very clear because congestion is usually concentrated at hubs, right? It's also a place where you can also have the most flexibility for recovery, but also that's where congestion almost always hits, right? Because these are big airports, whether it's there, you almost always have sources also emanating from these same airports. So it has the dual nature. With Southwest, I would imagine the model would be different. For example, Southwest, some concerns with Southwest are really its maintenance. So I would probably not even the source of its uncertainty. I would capture more on where will they find the maintenance path and revolve around that. The predictions, for example, I wouldn't just keep it around hubs because the operations are not as concentrated. So I would change that. So this is where knowing the system, and I said data-driven, model-driven stuff, knowing the system really makes a difference. How would you capture that? Of course, then you start to say, do I want a queuing model? Do I want a different way of capturing that uncertainty? Is it an uncertainty window, or is it a distribution, or what have you? Yeah. So again, there's no one answer there.
And I have another quick question for the second part for the UAV. We mentioned the emergency service, the application on the rural area. What about like thinking about let's say a eVTOL aircraft with pilots and let's say medical staff, or would that change the dynamics?
That's a really good question, and there are air ambulances existing now, as you know, but they are few and far between. Usually they've been used for transporting, like say, blood or heart or organs in very, very specific ways for specific needs or patients as well. But again, only for certain kinds of emergencies. I think with the rise of eVTOLs, we'll see more of that. But I would also imagine that you want to complement the advantages of these different aircraft. eVTOL with a pilot has certain positives. A drone has other positives. Again, it's about trading off which server, like the ambulance versus the drone. Now, if you expand that to include eVTOLs, now we would say, which one be more effective, right? Which depends on the type of emergency and what needs to be sent there. If it's an EpiPen, sending it is more important than transporting someone. So really, it would depend on the diagnosis, how confident are you in that diagnosis, and then which is the right server for that. This is where the other element of it comes. I spoke about the location aspect of the ambulances and the drones and stuff. The other is the dispatch. That's when you would start to say, which server do I dispatch for which thing? And how do I do that in the most intelligent way? So it's going to then be a combination of the dispatch models plus the location.
Excuse me, how tractable those disruption schemes are? I mean, how fast can you, because I'm seeing this type of decision as a operation decision, so it should come fast. And how tractable are those models? So,
The ones for airlines?
yeah,
Yeah, so that one we set it to solve for 2 minutes.
for like a whole minute
For the entire Delta Airlines aircraft. But you could split it up by fleet type, because like I showed you, A319, A320, you could split it up because aircraft recovery is done separately from passenger recovery and from crew. So, yeah, you can split it up. So, but yes, you're absolutely right. So we said, often 2 minutes is the time frame for making a decision, as soon as you observe the distribution.
Is that another place where you could do bound analysis, wherever if you go 3 minutes versus 5 minutes, do you improve the optimality of the result? Or is 2 minutes one of those places wherever you really start to see that plateau?
That's a good question. I mean, however, a lot of what's happening in practice is the practice time windows dictating, right? So really people prefer to make decisions or even await decision, but within that 2 minute time. So it's coming out more from, yeah, we'd like to do that. For example, that would turn out to be like a batching decision for your ride hailing, right? So if I wait for 3 minutes or so, I would get more information about demand and therefore I match better, right? So it turns out to be something like that. So if I waited for 3 minutes, one, I would get to know a little bit more about the disruption. Second, I would probably solve it better, hopefully, if we didn't solve the job. But in the case of airlines, often it's going by rule of thumb. So in that few minutes is not a big thing.
Okay, thank you.
Yeah, feel free to drop by my office or